problem 20 on page 113. And that is limit as x approaches 5 from x squared minus 25 over x minus 5. I'm given a limit, and I need to evaluate it or find it if you want. My first step must be to plug it in. Why? Here's one big reason why. Because I may plug in 5, and 5, if 5 is in the domain of this function, then the answer is 10/3, and I'm done. Now, if this number is not in the domain, then I still need to know what's happening here. So when I plug in 5 at the top, I get. When I plug in 5 at the bottom, I get. So at least there is hope. There is no guarantee the limit exists, but there is hope because it's 0 over 0. Okay, next step. I want to refresh your memory on the following theorem. When I divide 9 by 3, I get 3. What is the remainder?
0.
What does this mean? It means that 3 is a factor of 9. So from here, 3 is a factor of 9. Now, I plugged in 5 in this polynomial, and I got 0. That's really the remainder of the division. So x minus 5 must be a factor of the top. So I plug in 5 here, and I got 0. Of course, x minus 5 has to be a factor. So every time I plug in a number, and I get 0 over 0, the numerator will have a factor of x minus 5, and the denominator will have a factor of x minus 5, mandatory by the remainder theorem and the factor theorem. What if I have limit as x approaches -3 from p of x over q of x, and I get 0 over 0? Which is the factor that must come out from the top and the bottom?
X minus 3. Or plus 3.
Yes. So this must have a factor of x plus 3, and this must have a factor of x plus 3. So please keep this idea in mind. I'm going to come back to it again. So then you could say, why do I really need to think in these terms? This is too easy. X squared minus 25, I know how to factor. Why do I need to think in these terms? Because we may get something slightly more difficult. But every time you plug in a number in the polynomial and you get 0, that polynomial has a factor of x minus 5. If you plug in -3, the factor is x plus 3. So then all we have to do at this point is just factor the top, and you tell me what you get.
X minus 5x plus 5.
I can simplify x minus 5 because x is never 5. Otherwise, I'll have to state the restriction. And finally now, I have limit as x approaches 5 from x plus 5. No questions, no problem here. Why? Because this is a polynomial. And I have the theorem that says the limit of a polynomial, just plug it in and give me the answer. Plus 5.
10.
That's it. Any questions? Let's look at one with a radical and one with 2 polynomials that are not as simple as the previous one. So let's say 30. Limit as x approaches 1. I'm sorry, I think it's -1. Yes, x squared plus 5x plus 4. Everything divided by x squared plus 2x plus 1. slightly more difficult. I don't know what I'm facing. I need to plug in -1. When I plug in -1, what do I get at the top? So this will be +1 and 4, and this will be -5. 0. And the denominator?
0.
Yes, because this is +1, but -2. So there is hope. But I know exactly, I don't have to think. I plug in -1. I know the top and the bottom have a certain factor. Which factor for sure? Yes. So I have to have x plus 1 and x plus 1 coming from both. This is the problem. Once I remove the problem, the answer is a number. Although, I could have a square here, and then I get into a little more complicated situation. We'll see in a minute. So, I have the x plus 1. What is the other factor of the top?
X plus 1.
Perfect. I have the x plus 1 in the denominator. What is the other factor?
X plus 1.
Correct. So then I will be removing an x plus 1 from the top and an x plus 1 from the bottom. The new limit becomes, or function, is x plus 4 over x plus 1 as x approaches -1 from either side.
Where did the 5 go? Yeah.
Okay, let's do this together. X times x is x squared. Positive 4x plus 1x is 5x. 1 times 4 is 4. Very good. Good. So now what do I write? I plug in again, and what do I find at the top?
It's 3 over 0.
Okay, so then what do we conclude?
It's undefined.
We don't say undefined, but we say
DN.
DNE. Very good. Any questions on this problem? Any questions on this problem? Okay, so let's look at one more with a radical, so we can see that how that works. Oops, I forgot to count a label. Okay, so this was 7.
It got colder.
I'm sorry.
It got colder.
I know. I don't know what they did. I was hoping. Okay, so let's say 28. Limit as x approaches 9 from 9 minus x over the square root of x minus 3. Okay, the first step is very clear, which is I must, yes, the top will be
0.
perfect. The bottom will be
0.
okay, so there is hope. Notice that in problem 30, we started with hope, but it ended up being no hope. So there is no guarantee. But if it's a number, not 0, 5 over 0, we know there is no hope. And that situation has 3 possibilities. What are those?
A negative infinity, positive infinity, it's not the same.
Very good. Okay, so what do we do whenever we see a square root like that? Does anyone remember? We will the denominator in this case. We rationalize the denominator. By what? It means multiply the top and the bottom by the same quantity. So if we multiply top and bottom by the same quantity, this is nothing else but 1. But what do we need to multiply and then divide by?
X minus 9.
No, careful. Say it again. No. No. I'm looking back because we used this formula at the beginning of the class. So if we have the square of x minus 3, I need the
X
plus 3 to get the square of x squared minus 3 squared. Right? It's called the conjugate. We use the conjugate of the square of x minus 3, which is the square of x plus 3. Why? Since the square of x minus 3 multiplied by the square of x plus 3 will equal, can anyone give us the answer? First term squared, this is a minus b times a plus b. What is the answer? X squared minus b squared, which is x minus 9 indeed. So let's go back to the problem. Any questions? Any questions? Are you okay? Everyone? Yes? So we have the square root of x plus 3, the square of x plus 3. I will continue here. Can anyone give us the numerator? Do not distribute. 9 minus x, the square of x plus 3, over. We already calculated the denominator a minute ago. What did you say with the square of x minus 3 and the square of x plus 3?
X minus 9.
Very good. Perfect. We are close, right? When we plugged in 9 and we got 0, what is the factor that is the culprit? What is the problem? What factor is the problem? What factor is the problem? I don't even want to look at this. What factor is the problem that when I plugged in 9, I got 0? What is the factor that must go away?
X minus 9.
X minus 9, correct? So that's my target. In my head, I know that if this limit exists, and x minus 9 from the top must go away with x minus 9 from the bottom. But this is not ready. They're not the same. One has a negative leading coefficient that I have to pull out. So let's pull out the negative leading coefficient from the top. So this is limit as x approaches 9 negative. What is left in parentheses? Very good. And as we see, the problem is going away. Because now what we have is limit as x approaches 9 from negative the square of x plus 3. If 9 is in the domain of this function, then I'm done. If 9 is not in the domain of that function, then I'm not done. Is it? So what is the answer?
-6.
That's it. Do we all agree with -6?
Yes.
The square root of 9 is 3. 3 plus 3 is 6 with minus in front, -6. Is this okay? Yes? Okay. One concept here, and then we'll stop. Continuity. The concept of continuity. One theorem. A function is continuous everywhere if it is continuous at every what? Exactly. A function is continuous everywhere if it's continuous at every point. It's continuous at an interval if it's continuous at every point on that interval. So, is this function continuous? I graph the entire function without raising the marker of the paper. Is this function continuous? No, this function is not continuous. Is this function continuous? No, of course not. There are three types of discontinuities. So continuous, not continuous, not continuous. Three types of discontinuities. Two of them are right here in front of us. Jump, discontinuity. So jump. The second one is right here. It's called infinite. Infinite discontinuity. And there is a third one called removable. Only this is removable. This is removable. Why? Because I can define a new function and fill this in. But there is nothing I can do here. I cannot bring these two branches together. There is nothing I can do here. I cannot make this function defined at that point. But this one, I can remove. Using what I have, I can create a continuous function. But from the other two, I cannot. That's why this is called removable. Now, this is the concept that is the most important here. Continuity at a point. And then we can look at an example. So let's look at this function. And if I ask you, is the function continuous at 10, 6, what would you say? It does not have any of those three discontinuities. There is no jump, there is no infinite, and it's not a removable discontinuity. Is this continuous then at this point?
Yes.
Yes. Why? Three things have to happen. The limit from the left must exist. The limit from the right must exist, and they have to be the same. But furthermore, they have to be equal to what? To the exactly to the function value at that point. This time there is no saying, okay, the limit exists, the limit of when x approaches 10 from either side it exists. No, now I want continuity. So continuity at that point means the left limit, the right limit, and the function value at that point are all equal and they all exist. A function cannot be continuous if it's not defined at that point. So then, here is the definition of continuity. These three things have to happen at the same time. So the limit of f of x as x approaches a from the left must equal limit of f of x as x approaches a from the, and must equal f of a. Then I'll say f is continuous at x equals a. This is continuity at a point. 56 on page 115. We are given g of x, and you'll tell me what type of function this is. 1/2 x plus 1 for x less than 4. Negative x plus 5 for x greater than 4. It's asking us, is this function continuous at x equals 4? I have to show three things. I have to show the limit of as x approaches 4 from the left of g of x equals the limit of g of x as x approaches 4 from the right and must equal f of 4. If all these three exist and they are all equal, then I'll say yes, the function is continuous at 4. But let's analyze what happens here. And there is one piece of information that will give us the answer right away.
That would be
Exactly the domain. Exactly. What does the domain say?
4 is not a part of that.
4 is not a part of the domain. So this does not exist. So then is the function continuous at 4?
No.
No. I will say function g of x is undefined at x equals 4. Therefore, g of x is or is not continuous at 4. Is not continuous at x equals 4, of course. I have 3 minutes. I have time for one more problem and then I'll stop. 58. Same question. On page 115, we are given f of x this time. 1/3 x plus 4 for x less than 3, and 2x minus 1 for x greater than or equal to 3. The same question, is this continuous at x equals 3? I have to determine three things. I have to determine the limit from the left, limit as x approaches 3 from the left, from which branch? Exactly which one? Only one.
The 1/3
Very good.
x plus 4.
I have to show, or maybe not, that this is the limit of as x approaches 3 from the right, from which branch?
2x minus 4.
Perfect. And I have to show, I don't know yet, that this is the same with f of? Excellent. So can anyone, since these are polynomials, both, can anyone give us the answer for the first one? Yes. 3 over 3 is 1. Hold on. 3 over 3 is 1. 1 plus 4. That's okay. 5. Good. Can anyone give us the answer for this? Good. Can anyone give us the answer for this and tell me which branch will you use? Because you can only use one for x equals 3. The top or the bottom?
The bottom is 5.
Good. What do I conclude about this function?
Yes, it's continuous.
Definitely is continuous at 3. Because the limit from the left, the limit from the right, and the function value, they all exist and they're all equal. So f of x continuous at x equals 3. Because we showed